Okay, good afternoon, everyone. Okay, so as I mentioned, we're going to be moving on to chapter 4 today. So in the last couple of weeks, we looked at the solution of the elliptic PDEs. Now, elliptic PDEs had a steady state solution. So if you look at an elliptic PDE, it's not written in terms of any time variable. So the solution doesn't change over time. They're relatively easy to solve. Because they're not changing over time, we have a steady state solution. So whatever method we use, and we looked at Jacobi, Gauss-Seidel, and SOR, we're going to get to a solution. Okay, today we're going to be looking at hyperbolic PDEs. Today we're going to be looking at hyperbolic PDEs. Now these are the most sort of abundant in terms of the use of modelling and most useful. Essentially, because what hyperbolic PDEs do is they model things that change, model movement. So, for example, weather systems. We want to model weather or do computational modeling weather forecasting. Weather changes. Okay, you got pressures, you got densities, and they cause things. They are the reason why we have wind, the reason why we have rain, etc. So hyperbolic PDEs are perhaps the most useful in terms of modelling sense, but they also bring up a number of challenges for our numerical methods. Okay, so we're going to spend the next couple of lectures looking at hyperbolic PDEs. This is something I don't want you to worry about yet, but your assignment, which is going to be handed out at the end of this month, and that is handed in February, so you've probably got other assignments and deadlines before that. I don't want you to worry too much about that, but your assignment will be based upon solving a system of hyperbolic PDEs. So a lot of what we cover over the next couple of weeks will be relevant to the coursework assignment. Okay, as I mentioned, this is chapter 4 in the notes. Okay, hyperbolic PDEs model what we call propagation. In other words, things that move from one place to another. So fluid, so model, equations that model fluid flow are hyperbolic. Weather, aerodynamics, so things like a lot of F1 teams, Formula 1 teams use aerodynamic models to sort of improve their F1 cars. And if you want to design an aeroplane or design a car or a bike, you use a lot of aerodynamics. Blast waves, okay. Acoustics, you want to design a concert venue, you might want to take that into account. So lots and lots of different areas for hyperbolic PDEs. The independent variables are spatial coordinates, so it could be X, Y, it could be Z as well if you've got a 3D spatial domain, and time. Okay, so unlike the elliptic PDEs, which are steady state, hyperbolic PDEs change over time. Makes sense. If something's moving, it's going to move over time. Like always, solutions have to satisfy the PDE, the initial condition, and the boundary condition. So those three things our solutions have to satisfy. With hyperbolic PDEs, and this is not the case with parabolic or elliptic, solutions can contain discontinuities. You can have a sudden step or a sudden abrupt jump in the solution. So that's quite often seen in if you've got some sort of blast wave or acoustic wave. Because suddenly, if you think about acoustics, imagine you have a sound or a speaker, okay, and that speaker's turned off, and then you turn it on and put a sound through it. That sort of blast wave, that sound, is going to be discontinuity. Suddenly you've got no sound, or one time you've got no sound, then you've got sound. And the simplest of all hyperbolic PDEs is a PDE you've seen before. We looked at it in week 2, and this is the advection equation. Okay, and I'll talk about the advection equation now. Actually, before I talk about the advection equation, I'm going to bring up this diagram, which was in chapter 1. Okay, and this is the idea of the range of influence and domain of dependence of a hyperbolic PDE. Now, think about this point, right? This is, by the way, this is space and time. Okay, so across the horizontal axis, we have space, and on the vertical axis, we have time. So as we go up, you're moving forward in time. Okay, there's a point in our space-time, and the range of influence is what influence does this point have on the domain in the future? So if you take sort of horizontal slices, a horizontal slice is a snapshot in time. So as I go up from this point, I've got what's happening over time. So imagine, I go back to the thought experiment of having a swimming pool. Imagine a swimming pool being closed all night, the water's allowed to settle, and it's completely still everywhere. Now you've got up early in the morning, you've gone down to the swimming pool, and you see that you've changed into swimming cozy, and you see this lovely sort of flat water. What's the first thing you're going to do? You're going to do a massive bomb in the deep end. Okay, so that's you doing your massive bomb in the deep end. Now, when you do your bomb, you make the splash, you cause a disturbance, waves are going to propagate out from where you landed in the water. Now, at the other end of the swimming pool, the water's still going to be still, and it's going to be still until those waves propagate, that you caused, propagate out to that position. And that's what this sort of is showing. So there's you bombing into the swimming pool, okay, and we got waves going out. So imagine the waves propagating out like that. And so a position over here, which is at the other end of the swimming pool, a short time after you jumped into that swimming pool, it's still not going to feel that disturbance yet. As we go up into time, it's going to start to feel the disturbance. Okay. These diagonal lines, that's the fastest and slowest possible speed that what we're modeling can move at. Okay, so imagine if this was acoustics, you've made a sound. Okay, these will be the speed of the gradient, and these will be the speed of sound. Okay, they could also be speed of light. That's where you get the idea of black holes from. And if you're into physics, that's what that governs. Okay, so the range of influences, what effect does us jumping in the swimming pool have in the future? The domain of dependence is kind of looking backwards, looking back in time. Okay, what events occurred back in time that affect our point in space and time there? Okay, so we could have had other disturbances in the pool. Okay, or so something happened there will still affect that point in space and time. Right, so let's go back to the advection equation. As I mentioned, simplest of all hyperbolic PDEs. Okay, so we have U, which is some dependent variable. U is a function of time and space. So it's a function in the 1D case of x and t. Okay, t is time, x is space, and v, this is sort of, it looks like a U, but it's meant to be a v. This is v, and that's velocity. Okay. What this models is movement of something from one place to another. Okay. And how fast that thing moves from one place to another is given by the velocity v here. So this model is what we call pure advection. It doesn't change what we're moving. Okay. If you have a shape, it'll move it down the domain, and the shape will be retained. So, for example, let's say I'm stood at the side of the river's flowing in one direction, and let's say I was to dump some pollutant in the river. That pollutant would flow with the speed of the river downstream. And with the advection equation, it would just assume the shape of the pollutant as I throw it in would just maintain. Now, in reality, that wouldn't be the case. It's a very simple model. If the initial conditions, remember U is a function of time and space, so when time is 0, so we just got a function of space, so the initial conditions is equal to some function f of x, then the exact solution is simply f of x minus v times t. In other words, something's moved downstream. Okay, this is unique, well actually, sorry, I shouldn't use the word unique. This is unusual, because we have an exact solution to a PDE. I keep saying that exact solutions don't exist, well, this is one of the exceptions to that. And because an exact solution exists, we tend to use this equation to test our numerical schemes. Okay, ordinarily, this equation doesn't model, it's not very useful for modeling anything, but it's a useful test. Any scheme which doesn't perform well on the advection equation is not going to perform well on some more complicated and sophisticated equations. Okay, so sort of pictorially, what's happening? Well, here I have, let's say I've got a one-dimensional domain here, and the red line is some initial condition. So it doesn't matter what it is. So that's my initial condition. After t seconds, or after time t, is the blue line represents that solution after time t. So the same sort of triangular shape has just been propagated along the domain. That's assuming that v is positive. If v is negative, it would have gone to the left. Okay, it would have gone in the negative direction. Because in this case, if we assume v is positive, it's gone in the positive direction. So that's what essentially what the advection is. Okay. So what we're going to do now is we're going to look at solving that advection equation. Okay. Exactly the same method as we saw with Laplace's equation last week. We replace our derivatives with finite difference approximations. So what I'm going to do is I'm going to use a forward difference for the time derivative. Okay, that's first order forward difference there. Remember the n+1 superscript. That means what's our value of u in the next time step in the future, and that's the value of u in the current time step. Okay, and I'm going to use a backwards difference for the x derivative. So you notice here the subscript I, ui is sort of like your current node, but you're interested in ui-1 is the node to the left. Okay, so now we've changed it from a differential equation to an algebraic equation. And all we do is we rearrange, and what we want is we want this n+1 term to be on its own on one side of the equation. Okay, so subtract the second term from both sides, multiply by delta t, and add ui, we get down to this. Okay, so very similar, excuse me, very similar to what we did last week. Okay, so this is our finite difference scheme. As you can see, all of the superscripts here are n. It means these are current known values. The superscript on the left-hand side, n+1, this is a future value. This is what we're going to calculate. We know all these numbers, and we're going to calculate the future value based on those. Now, in this case, we approximated our finite differences using, approximated the derivatives using first-order finite differences. Okay, so therefore, we say the truncation error for this scheme is first order in time, because the power of delta t is 1, and first order in space, because the power of delta x is 1. If we'd have chosen different orders of accuracy of our finite differences, we'd have a different scheme. We'd have a scheme which is not the same as that, and we'd have different accuracy. Depending on how accurate you want, depending on the problem, you might choose to have a more accurate approximation of your derivatives. But for now, for this purpose, we're just going with first order. Okay, and there's the stencil. So remember, the stencil is kind of a pictorial representation of the information required of the scheme. So there was our scheme. And we're saying, okay, if you imagine left to right is your x-axis, up and down is your time axis. So as we go up in time, the time axis, we're going forward in time. Okay, we want to calculate this value. Well, this value is dependent upon its current value and the value to the left. Okay, so this gives us this stencil. Now, if the velocity is positive, that means our advection is going from left to right. So if you think about it, if we're calculating that, the change is going to occur from the left. Okay, so this node will experience the change before that node. So this is fine. Imagine this scheme is looking. Imagine this scheme is a human. I know it's a bit weird, and it's looking to the left. Now the change is occurring from the left, therefore the scheme can see it coming. Now if the velocity was negative, the change would be coming from the right. So we'd have something moving from the right, but as it stands, this scheme wouldn't see it coming, and it wouldn't be able to deal with it. Okay, so if you had the velocity was negative, we have a problem. We couldn't use this scheme here. Okay, so what do? Well, instead, we use a forward difference, excuse me, for the spatial derivative. So we use a forward difference for time, which is the same as what we had before, but this time I'm going to use a forward difference. Still first order, we haven't improved any accuracy. Okay, so if I use a forward difference, we have this scheme. So instead of, if I just show you the previous scheme, here we have ui minus 1. So we're looking to the left. Well, with the forward difference, we look to the right. Okay. Same accuracy, so we haven't gained any accuracy, but if our thing or whatever we're propagating is going from right to left, this scheme can deal with it then. So depending on whether you got a positive or negative velocity will depend upon whether you use a forward or backwards difference in space. Okay, so that's sort of, both of those schemes are what we know as a first order upwind. The reason it's called upwind, the upwind direction is the direction from where we expect the change to come from. Okay, so if velocity is positive, the upwind direction is from the left. If the velocity is negative, the upwind direction is from the right. Okay, so this is called first order upwind, or FOU. It's the simplest of all finite difference schemes for solving the advection equation. This is what is known as an explicit scheme. In other words, I know all of those values here, so I can explicitly calculate our next value, un plus 1. Application of these schemes calculate the solution of the next time step using the current time step. So you're stepping through time. So you've got the current solution, and we step by delta t to get the next solution. Then when we've got that, we step again to get the next solution. So it's often called a time marching scheme or a time stepping scheme. Okay, so we're going to be looking at testing our first order upwind scheme. And I mentioned before that the advection equation has an exact solution. And what I'm going to do is I'm going to test it over a spatial domain that goes from 0 to 1. So my domain starts at x equals 0 and finishes at x equals 1. So what I need is initial conditions and boundary conditions. I'm going to say my initial conditions is given by this Gaussian function. You know, in statistics, you have the bell-shaped curve, normal distribution. That's essentially a Gaussian function. It's an exponential function minus 200, x minus xc. Now, c is the center of my sort of curve, and that's all squared. I think you've seen that before in week 1 in the lab exercises. In this example, I'm using center of curve as being 0.25. Okay, I'm going to use Neumann boundary conditions, which are transient or transmissive flow. This means any propagation would just flow out to the boundaries as if they weren't there. It's what we call a semi-infinite domain. Okay, so how we do this is we have a ghost node, so the left-hand ghost node. Remember, this is a node which is outside of my domain. I'm going to set it as the second node within the domain. Remember, the first node is U0. Okay. So if I set our ghost node equal to U1, that means the gradient across the left-hand boundary is 0. And the same thing at the upper end. So the UN plus 1 is my ghost node to the right, and I set that as my penultimate computational node. So this assures that the derivative at that right-hand boundary is equal to 0. Now the exact solution, there's my, if you think about it, that right-hand side there is my f of x. The exact solution is f of x minus vt. So all I do is replace x with x minus vt there. And that will give me an exact solution. Advection velocity. And we're going to calculate solution over the range 0 to 0.5. Okay, so there's my initial conditions. Okay, so the centre of the Gaussian curve is in this case at 0.25. I think I might change that in the notes. So I'm going to double check. Yeah, I think in the notes I changed it to be a half, but it doesn't really, in terms of what we're doing, it doesn't really matter. That's my initial conditions. Using a velocity of 1, after half a second, my initial condition, or my Gaussian curve, is propagated from left to right, because we've got positive velocity, and it ends up there. And the dashed line is where it sort of started at. So I know the exact solution. My numerical solution should, or hopefully, be very similar to that exact solution. Okay, solution procedure. What are the sort of mechanics of our solver? You start by initializing all your variables. So what's your velocity? What's your time steps? What's the domain, etc. And you calculate your x array, which is your coordinates of your finite difference nodes, and u0, which are your initial conditions, which in this case was that Gaussian function. And then what you do is you loop through your solution method. Okay, so whilst n is greater than n steps, or whether, if we've got to keep going, you calculate your boundary conditions. So remember, we're using transmissive boundaries. You calculate your scheme. We're going to be using the first order Upwind scheme, and then you update your solution. So your UN becomes UN plus 1. You've updated it and ready for the next iteration. Going to override that. You increment t by dt, or delta t, okay, and you add 1 to your counter if you use one. And if you want to, you can plot it, and that will give you an animation. Okay. Discretizing the domain here, sometimes it's really useful to actually draw diagrams of what's going on. Okay, we got a 1D case. We got a boundary at the left-hand end, and that's where our first node, our node 0, is, and the boundary at the right-hand end is where our node n is. Outside of the boundaries, we have ghost nodes. Okay, these are the first positions. So let's say we're using 100 nodes or 101. Some people say 101, some people say 100. In other words, you divide in your length of your domain by that 100. So your delta x is 0.01. So my coordinates, the ghost node will be minus 0.01. My node 0 is on the boundary. The first node in from the boundary is at 0.01, then 0.02, etc. Up until sort of like the penultimate node, the final computational node, and we have the ghost node as well. Okay, that's the discretizing the domain. Okay, how many steps do I need to take? Well, for the advection equation, we're going to use a constant time step. That's not always the case. When we start to look at nonlinear systems of PDEs, we have to change our value of delta t at each step. But for the advection equation, for now, our delta t is going to be constant. The number of time steps required, okay, is b minus a over delta t. So b is the point at which you want to finish your simulation. A is your time where you're starting the simulation. Okay, in this case, we're going to use a delta t of 0.009. and there's a reason for that. I'll explain shortly. And we're going to calculate it up until 0.5. T is 0.5. We're going to start T is 0. Okay, so we're going to take 56 steps in total. Okay, I'm not going to bore you with all the in particular sort of individual calculations, but that's what we get. Okay, so there's the red line is the exact solution. The blue dots are each the approximated or computed solution. Okay, so as you can see, we're not quite bang on the line. Okay, we have this sort of smoothing out of this sort of the tail of our Gaussian curve, and we also have this gap here. This is called dissipation. So what's happened is our numerical scheme can't quite deal with this area up here. Now that's a common feature of first order schemes. Behavior is a feature of first order schemes. So in essence, first order schemes aren't good enough. Okay, but I'm using them as an example here. Okay, so that's a first order upwind scheme. So we can see here, we've got dissipation, numerical dissipation. So, sometimes dissipation is built into PDEs and we want it. In this case, we don't want it. So we've got to find a way of improving this bit here. Now, the dissipation is a feature of a first order spatial derivative or approximation, a first order approximation. So the obvious solution would be to use a second order approximation. Okay, so going back to the PDE, the advection equation, what I've done here is instead of a forward or backwards difference, I've taken a central difference. Okay, so node on the right minus node on the left over 2 times delta x. That's your second order difference. You should be familiar from that from lab sheet 2. Do the same thing, rearrange, and this is our scheme. So you can see, well, if you compare it to the first order upwind scheme, a couple of differences. One is we've got the 2 delta x on the bottom here, whereas before we only had 1 delta x. And in this case, we're using both the left and right neighbouring nodes. So in this case, it doesn't matter whether v is positive or negative, we're going to see it coming from both ways, so to speak. And this is first order in time, because we've still only used the first order approximation for the time derivative, but it's second order in space because we've used the central difference. Okay, so this should be better. Okay, and this is known as the forward time central space scheme. Obvious reasons, we've gone forward in time, central in space, or FTCS. And here's the stencil. As I mentioned, we use both neighbouring to the left and to the right. So there's no need to consider which direction is the upwind direction. And that's what happens when you run it. Okay, we're not quite doing the... Well, actually, this is what happens after a very short... We've only gone 1/5 of our solution time. We wanted to go up to 0.5. Well, I've stopped it after 0.1 because something's not right there. Something's going wrong. So here we have, remember the red line is what we're trying to approximate. We've got the blue line, and it's going a bit bananas. This is what we call an unstable scheme. Okay, so what's happening here is the numerical scheme is producing oscillations, and you know, the up and down squiggly bits. Those oscillations will keep occurring, and eventually it will just crash the computer. So I've stopped it artificially. Okay, so the forward time central space scheme is unstable, and we'll be looking at the idea of stability next week. Okay, right. Have a look at base 62. Okay, we're going to have a look at a worked example of solving the advection equation. Okay, so one of the reasons why I'm getting you to do this worked example is when you coded up your scheme or you coded up in MATLAB what you're doing, how do you know what your code is producing is what it should be producing? You may get output, you may get some numbers. How do you know they're correct? Well, an important step is what we call verifying the code, making sure that code is doing what it's supposed to do. And what we do is we do a reduced sort of set of computations and just check it. Check what you got by your hand calculation compared to what MATLAB gives you. Okay. So here we have concentration of a pollutant in the river is modelled using the Advection equation. And we're taking a 10-metre stretch of the river. We're going to model, and the flow velocity in that river is 5 metres per second. At time t equals 0 seconds, a pollutant is released into the river, and the shape of the pollutant can be described by this case statement. So in other words, between 2 and 4 metres in our stretch of river, our pollutant concentration is going to be 1, and elsewhere we're going to have no pollutant. Okay, so first one is draw a diagram of the finite difference group for this problem. Now this, those of you who know me from sort of graphics last year, I'm always saying have a scrap piece of paper next to you whenever you do any sort of work on the computers. Really does help. And so drawing the diagram, what we have is we have a one-dimensional line. That's our sort of spatial domain. And at one end, we're going to have our left-hand boundary at 0 metres, and we're going to have our right-hand boundary at 10 metres. And our velocity is 5 metres per second, and it's travelling in that sort of direction. Okay, so that's our domain. We're going to discretize that. So we're going to have a node at the left-hand domain, that's our U0. We have a node at the right-hand domain, that's our UN. In this case, it said use 6 nodes, so that's going to be U5. Okay, so we're going to have 0, 1, 2, 3, 4, 5. That gives us 6 nodes. And so if we've got 5 nodes, our spatial step is going to be 2 meters. 10 divided by 5. Okay, so we're going to have 2, 4, 6, 8. Okay, and that's going to be U1, U2, U3, and U4. We should also actually put in ghost nodes. So sort of down here on the left, we have a ghost node, and sort of somewhere up here on the right, we have another ghost node. We're only really interested in the solutions U0 to U5. The ghost nodes are just helping us with those boundary conditions. Okay, so the first order Upwind scheme, well, we know we're going to be using a constant time step of 0.25 seconds. And we know that the velocity is 5, and we know delta x. So we can calculate v times dt over dx, or v times delta t over delta x. The reason I'm calculating this is the coefficient in our scheme. Okay, that's going to be constant. There's no point keeping calculating it all for different values. Okay, so v is 5, delta t was 0.25, and our delta x is 2. So what does that give us? So 5 times 25 over 2, 0.625. I should really explain why did I bother calculating that. If I go back to the first order Upwind scheme, here you can see v times dt over dx is multiplied by our nodes. This is going to be constant, so I might as well get that out of the way to start with. Okay, so then therefore our first order Upwind scheme can be written as follows. all of a sudden it doesn't look too difficult. So your value of your node I for the next time step is equal to the current value minus 0.625 times the current value minus its neighbour on the left. Right, so we've got boundary conditions, we've got our PDE, we've got our velocity, we've got a time step. The next thing we need is initial conditions. And the initial conditions in this case are given by this statement up here. So when x is between 2 and 4, our initial value is 1, else it's 0 elsewhere. So nodes U1 and U2 have coordinates 2 and 4, so those two will have a value of 1. All the other nodes will have a value of 0 to start with. 0, 1, 1, 0, 0, 0. So in other words, that's where our pollutant is at the moment. And what we'd expect to do is it to sort of propagate downstream. Now what we do is we calculate our finite difference scheme. Okay. So for this node, U0, we have the current value 0 minus 0.625 times the current value minus whatever the ghost node is. Now I'm going to use U1, actually, I'm going to use the ghost node is going to be equal to U0. So whatever this node value is, the ghost node is the same. So what that means is that node minus 0 itself means all of this will be 0. So I'm not going to bother calculating that, that'll be 0. So in other words, we have 0 minus 0.625 times 0 minus 0. Just everything 0. Okay, now we've got this one. Okay, so if I follow this scheme, we have 1 minus 0.625 times 1, which is UI, minus node to the left. Okay, so our value is going to be 0.375. They do the same for this one. 1 minus 0.65 times 1 minus 1. So it's that value minus that value, and that's obviously 1. And do the same for this one. So 0 minus 0.65 times 0 minus 1. 625. And the other is going to be 0 because you just got 0 minus 0. So after one time step, you can see our pollutant is starting to move downstream. Go for the next one. Well, that's going to be 0 again. So here we've got this one, which is 0.375 minus 0.625 times 0.375 minus 0. That's 0.1406. Just worked for this one, please. Okay, keep going. So next one we have 1 minus 0.65 times 1 minus 0.375. So 94. So I worked for this one places. And keep going. .8594. 0 minus 0.65. 0 minus 0.3906. And that's really 0. So you can see after 2 time steps, we're slowly propagating downstream. Okay, last one, might as well do it. So we have 0.1406 minus 0.65 and 0.1406. So 0.0527. So this one, the value of this node started at 1. As you can see, it slowly decreased as what's propagated has disappeared downstream. And in this case, 6094 minus 0.625 times 6094 times 0.148. 3164. And keep going. And that'll be 0 as well. Oops. And that will be 0. Okay. So that's a very sort of simplified, only using 6 nodes. In practice, you'd use at least 100. But if you do code this up in MATLAB and you use 6 nodes, you should get the same results. So it's useful to be able to check your MATLAB code works against a reduced domain. And essentially, it's going downstream. What should happen is the height, well actually the ideal solution, well the height should be 1. So you should have that sort of step going downstream. What's happening with the first order upwind scheme is it's starting to dissipate. Okay, that's a feature of first order schemes. Let's have a look at the forward time central space. Now with the forward time central space scheme, we have VDT over 2dx. Okay, so in other words, it's whatever that is divided by 2. Okay, so our scheme is the current value minus 0.3125 times the node to the left, node to the right minus the node to the left. So there's a subtle difference between first order upwind and forward time central space. And go ahead and fill out the rest of this table. So the initial conditions are exactly the same. Maybe 0, 1 minus 0.3125 and 1 minus 0. Okay, and this one is going to be 0 minus 1. So we're going to have 1 minus 0.3125 times 0 minus 1. So we're taking the node to the right minus the node to the left. Okay, 3125. And if you carry on, here's one I did earlier. Right, okay. So you can check those, or you can do them in your own time, but those are the ones I did earlier. Okay, so the forward time central space scheme, there's an early warning here. Okay, that number is bigger than our initial concentration. Okay, so somehow we've improved.
You know the change in x is 2, so 2 times 6 4.
Sorry?
You know the bit in where it's like change in x?
Yeah.
2 times change in x. Is that
yeah.
just 2?
Oh, where I got basically all I did here, because I've already done sort of that calculation. Let's divide by 2. So give me that one there. So that's sort of what it meant. Okay. So already I got an early warning sort of thing. Hang on, I'm increasing my amount of pollutant. And also down here, we get in minus numbers. Now you can't have a negative quantity. It doesn't exist. The idea of a negative quantity, you know, it's sort of the universal implode in that case. Okay, so this is an unstable solution. It's useless. Forward time central space scheme does not work for the advection equation. Okay, so why did I bother saying, okay, let's use a forward time central space scheme? Well, essentially, it's a essentially it's not seeing anything. Nope. Anything? Oh, try again. I've broken it. Try once more. Oh, that was working. What about? It's all in. Give me 2 seconds. They love it when technology doesn't work. So, what's going on here? Right, give me a couple of seconds. I don't know what. Ah, whoa. Oh no, that was. All right. Try again. If not, I'll just have to go old school. Oh, that's a shame. No, it's not working. Okay, I'm gonna have to